And they're saying now that yearbook is they aren't going to have like half. They don't have like half of the school year.
All right, you guys. So. All right, you guys. So remember we left off force vectors, didn't we?
Yes.
Yeah.
Let me.
Oh.
Yeah, we didn't get terribly far in, but that's fine. Okay. You guys, the one housekeeping thing that I need to announce to all of you guys, across my classes, I've been having a lot of issues with phones. You guys have not been bad. This isn't a reflection on you. But in all my classes, I'm dealing with phones all the time. Reminding kids to put it away, put it away. I take it for the class. Well, they show up to my class the next day, they're back on their phone. I'm teaching, and they're on their phone. Well, then they ask me what's going on. I was like, where were you for the last 30 minutes? I just explained it. When I give work time, kids just sit there on their phone, and then when I come over, they like hide it, and they haven't done anything for 30 minutes. So it's really frustrating for me to waste my teaching time when nobody's paying attention because they're on their phone. And it's super frustrating when I give students time to do their work, right? Sometimes it's in-class stuff, my other classes mostly, or it's like, you guys have an hour to do this assignment. It's due before you leave. If you do it, you get points. And they still are on their phones all day. So I'm cracking down on phones, and I'm going to enforce, again, the school's policy is no phones in the classroom. My classroom personal policy is no phones. Unfortunately, I've had to crack down, so if I see a phone, if I see you on a phone, I'm going to take it, write your name on it, and I'm going to send it to the office, and you'll get it at the end of the day. I don't want to do this. I don't want to have to be taking phones from you guys. But you guys, not you guys in particular, all of my students have just given me no choice. I can't continue to waste my class time with phones. So please, put your phone in your pocket. Put your phone in your backpack. Make sure it's on silent. Just put it away and leave it away while we're in class. There are going to be times, especially in this class, when I'll say, hey, today's lab, you're going to actually need to record a slow-mo video. You can use your phones. Or, hey, today you're going to need to do some calculations in lab. I'll let you use your phone to do calculations. At those times, I've given you permission. Otherwise, just keep it away. And I hate to waste time explaining all this, but I want to be crystal clear. If I see a phone, I'm going to take it to the office. I just have to nip this in the butt because it's such an issue in all of my classes. So anyway, I just want to be clear on that. Okay, back to physics. Where did we leave off?
Right here.
Yes, we got the test from Unit 1, kinematics, wrapped up. You guys all should be content with that score. Getting that group test. I wish you guys would have talked more. But again, I wanted to give you guys an additional chance to take that assessment. I will not be using the AP progress checks for an assessment anymore, right? I think we'll use them as maybe practices. So like a week before we have our test, I'll say, hey guys, do the progress check. See how you do. Not graded, it's just something for you to practice. Practice even some of those really challenging AP questions. But then I'll make my own tests for the units moving forward, okay? So I'm glad we wrapped that up. Now we're trying to pick up speed to get on track with Unit 2. We're in Unit 2 right now. What unit are we in? To help us keep track. Unit 1 was kinematics. It was just motion, the equations for motion, acceleration, position, velocity. What are we doing now? Force, yep. What? Yes, dynamics. Dynamics is the blanket term for this unit. Dynamics, all that means is kinematics with forces involved. We're going to do kinematics. We're going to look at motion, an object's position, velocity, acceleration. But now we're going to consider, how did that object move? What force caused that object to move? What force is causing that object to accelerate? If an object's not accelerating, what forces are absent, right? So all we're doing is taking kinematics and we're adding forces in force diagrams, force vectors, Newton's laws. We're going to learn about those in this unit. So that's really what this unit is. It's just continuing the kinematics. So we've talked about a lot of this stuff, right? We want to analyze a force. The red, this is the actual force applied in real life. He's pushing in this direction. When we analyze it, you're good. I'm not having that though, by the way. Thanks, Brody. Again, I'll post the homework so you'll have it. You got a worksheet, and then just watch the recording for the rest of this, and you'll be good to go and back on track for Monday.
Yes, sir.
Thanks, Brody.
You're welcome.
When we analyze this, the same as we did in kinematics, we take the 2D motion and we split it into parts. We want to look at just the component in the y direction and just the component in the x direction. These are the components of the force vector. These two imaginary pieces add up together to create the actual force we're interested in. All right? SOHCAHTOA. We need to remember this. This could be something that you just know, remember, and as soon as you get your test, you're writing that down, so you will not forget it. If you write SOHCAHTOA, you can figure out all the trig functions from this, right? So, what's the equation for sine? Remember? What?
Opposite of hypotenuse.
Exactly. Sine is opposite over hypotenuse. What's the C stand for?
Cosine.
Cosine. Cosine is the second trig function. Cosine is adjacent over hypotenuse. What's the third trig function? Tangent. Opposite over adjacent. So if you guys are new to this, SOHCAHTOA, write that on your test, and it tells you what the equation is. I'll tell you, I always go to the original. If I see my angle and I'm trying to break it up, I'm like, okay, there's this angle. I want the opposite side, and I know the hypotenuse. I literally write sine of an angle equals opposite over hypotenuse. I do it every single time, and then I calculate my equation. So I write this every time, plug in what I know, and solve for the unknown. So you guys can all do this. You can write SOHCAHTOA, you can write the equations, and then you won't forget them and you'll just remember them. SOHCAHTOA is that key to figuring it out. So I think we're working on this one, weren't we? We did? We did this one too? Okay. See, they skipped steps. They said the sine of 27 is opposite over hypotenuse. They multiplied that to the other side, and what you're left with is your unknown. I never skip steps. I always write the original, because that's my method. I trust myself to repeat that process. Once I have the original equation, right, once I have this, I know how to do algebra. So I don't make it hard on myself. I start from the beginning and then just do my algebra. So I think we're at this part now. What happened is, instead of having the force be applied in this direction, we changed, so now the actual force is straight down. Well, it's acting on that ramp, right? They're going to put a ball in here. This is gravity, right? This object has a mass, and gravity is trying to pull it to Earth. Gravity always wants to pull things to the center of the Earth. So the weight of an object is the force of gravity on this object. Well, we can split that object up into the x direction along our ramp, and then a y direction perpendicular to our ramp. Again, we'll work on inclined plane problems more. This is a bunch of trig that they're doing. They said if you know the angle's 27 degrees, you know this one's 27 degrees, because these are similar triangles. Here's my 90 degree for the incline ramp. Here's my 90 degree for the components of my forces. Now I have my triangle. I would do the same thing, right? Sine of 27 is opposite over hypotenuse. Well, I know everything except this value. Calculate it. That's my force component in the x direction, or the ramp direction, because that's meaningful to us. We can use that. Then you do the same thing. Cosine of 27 uses adjacent over hypotenuse. Well, I know everything except the adjacent, so I can just do my math and figure out what component is acting into the ramp. Right? What would equilibrium mean? We've been talking about forces. If I throw this word out, we know it's related to forces. What does just the word equilibrium mean in general?
Like the balance between things.
Yeah. We have an equilibrium. There's a balance. Things are equal and in balance. When we talk about forces, an equilibrium of forces means the forces are balanced. If I push one way, right, if I push in the x direction, if there's something pushing in the opposite direction at the same magnitude, they're in equilibrium. They're balanced. Do you guys know? Oh, I have one up there. This one's good. You guys know what this is? Yeah, the scale. Right? This is old school. You guys ever been to the doctor? They have the one you stand on and they have this weight that they like notch over and then it levels out and that's what your weight is. That literally uses equilibrium to tell you how much you weigh or how much mass you have. This is looking at how the two forces on both sides are balanced, right? I'm going to see if I can actually demo this for you. I'm going to use this roll of toilet paper. I got to make sure I...
Best part about that.
All right? So this scale works by figuring out when are these two balanced. If I put something on here, it's out of balance, right? If I put my toilet paper on one side, there's not a balance for the other side. Well, then I move my hanging mass, and I go until it's starting to balance. You see that? That's pretty good. And then you can see if too much. I'm not balanced yet. You guys should remember this at the doctor, right? They sit here and they fiddle with. Ooh, that looks good. And also you can see this needle up here tells me how accurate I am. That looks good. So my mass, back here I have 60 grams plus, this is 61.1 grams. When I have this mass, which is a known mass, balanced with this object, when they're in equilibrium, the force pushing down from the toilet paper and the mass that I push on the other side, when those are balanced, that's how I get my mass measurement, my reading. That's an equilibrium. The mass that I put on the scale pushing up on this side is balancing what's pushing down on the other side. So that's an equilibrium. Now we're going to get a lot more in depth on what that means. And we're also going to use that to solve our problems, right? When we balance the forces, this will become your lifeblood in physics. This is like a core equation and a core tool when we do physics. We always want to know equilibrium. That's when all the forces add up to 0. That would mean they're balanced, right? They cancel each other out. The net force is what you call the leftover. If I have two forces, they're going to add up to be the net force. If I have two forces opposing each other, if they cancel out, that means my net force, the total, is 0, because they're equal and opposite. What force is acting on this girl hanging from the monkey bar? We know we have gravity, right? She's hanging. Gravity's always trying to pull objects down to the center of the earth, right? Gravity is pulling on her mass and trying to pull her down. Well, we said, right, in the y direction, this is positive, that's negative. So gravity is pulling on her with 60 pounds in the negative direction. Well, if that was it, wouldn't she drop straight to the center of the earth? If you push down, the object moves down. How is she hanging there? Where is she applying her muscles? To the bar. She's holding herself up on this bar. What forces is she using? She's got 2 of them, right? Her 2 arms. In order for her to hold herself steady, to be in equilibrium, her arms need to balance gravity. So each of her arms is pulling up at 30 pounds. This is why a one-armed push-up is insanely difficult. If I only use one arm to try and pull myself up, all of my weight has to be held by my single arm. When I use 2 arms, each arm only has to do half of my weight. That's why we do pull-ups with 2 arms, and it's so difficult to use one arm. Let's sum the forces. I have a negative 60 and 2 positive 30s. Well, negative 60 plus 30 plus 30 equals 0. If my forces sum up to 0, I am in equilibrium and I'm balanced. I'm not doing anything. I'm just hanging there. Right? Would it be? That's a great question. Say this girl had a 3rd arm that she could use. Would it be easier? Huh? That's a great question. Let's answer that.
I'd say yeah. 20 pounds an arm.
Evan thinks yes, it would be easier. What'd you say, Josh?
Yeah, it would be because it'd be divided 20 pounds an arm.
20 pounds per arm? Do we agree with that?
Yeah.
Yeah. If she had 3 arms to pull herself up, and they're all equally strong, each arm would only need to pull 20 pounds. So you could be really weak, right? Each arm is pretty weak, but if you had 3 arms, you could do a pull pretty easily. Because you'd have 20, 20, 20 to balance your 60. Right? That's a great question.
It's kind of a weird question, sorry.
That's all right. Well,
now, what if she had 5?
she's like a Men in Black alien. This is her disguise.
Josh, would you rather have 3, like, average arms
Wait a minute.
Whoa!
How did you do that?
I actually had no idea. That's actually amazing. I should have played that off, dang it.
Wait, what happened?
She got
He asked the third arm question. I went to the next slide and.
You already had it prepared.
Oh, so you already.
Bingo! Now we're doing physics. Yes.
It's almost
So,
like from the first Men in Black, like how he's out there and all those people are shooting out all those like cardboard cutouts of aliens, and he shoots like he shoots the little girl, and he goes, "Well, why did she deserve to die?" And he said because what girl is out there with her textbook this thick at 10 o'clock at night?
and that was an alien.
Yeah, he said that. He thought she was.
Anyway, it's exactly right. If she had 3 arms, there's 3 places that she's applying a force. So each force only needs to be a lot smaller to be in equilibrium and to counteract gravity. All right? So let's try to solve this one. We put an anvil on the table. The anvil, gravity pulls the anvil with a 90-pound force. The table itself weighs 20 pounds. Well, if we are told 50 pounds is on this leg, 30 is on that leg, 20 is on that leg, well, shoot, how do we do this? How do we figure out what the last leg is?
You add up the weight of the leg, you add up the weight of the table and the anvil.
You have 100. You have 100.
You find the difference.
So I'm hearing adding up the weights, right?
Well, wait. You'd have
All the
Yeah,
right. This force is going up, isn't it?
Yeah.
All these forces that are supporting the table and anvil, they're pushing up to counteract the anvil and the table. Well, how do I use equilibrium? What does equilibrium tell me has to be true?
All of those have to be equal to the weight of the
Equal to what?
0.
The sum. Yes, 0. You guys know this Greek letter? Have you seen this before?
the form.
It's a Greek capital sigma. This is the capital letter sigma. You'll see this a lot. This means the sum of. The sum of the forces equals 0. That's all equilibrium is. All our forces are in the y direction, right? They're all up and down. So we can even do this. All our forces in the y direction, so we're going to do our equilibrium in the y direction.
The other leg would have to be 10 pounds then.
Well, yeah, let's see. What force should we start with?
That'd be 90 pounds.
Negative 90, right?
And then you'd have an extra 20.
Okay.
So that gets you minus 110.
Let's add them all up, though.
Yeah, as I
Plus
said.
50.
Oh, wow.
Plus
You can do it that way.
I
Plus
was thinking
30,
about just adding up the
plus
positive
50
and
would be 0.
Plus 50.
Plus 20.
plus 20,
Plus
plus unknown. So these are negatives, right?
Yeah, and that's negative 110. And you get positive 100.
6, 7, 8, 9, 100.
That's why the other leg would be 10. That's why I was saying like adding positives.
Yes.
Adding negatives.
And that is a good strategy.
Because I feel like it would get more confusing. Because if you have like a lot of numbers going
Yep.
on, then
You're
it
right.
would get confusing so you can know what's going on.
Yeah, Josh is making a good point. He was saying, well, add up all your negative forces, add up all your positives, and then just leave your unknown off to the side and see how the negatives and positives cancel each other out. Well, this creates negative. Let's make the equation do the work for us. This negative 100 and 100 is negative 10, right? We still need to add our unknown force, and it has to add up to 0. Well, what's my next step algebraically? Add 10 to the other side. Unknown equals 10. What are my units? Pounds. So this, bingo.
101 BS.
101 BS.
No. So this is how we use equilibrium. We'll always start here. You'll write this over and over and over and over and over again. You'll always start there and just start adding up your forces. It's really simple. It's just an algebra equation, but you have to know what it's meaning. All right? I'm going to skip the rest of this for now. We'll come back later. Now, we're going to do, Newton's first law. Would anyone happen to know Newton's first law?
Object in motion stays in motion.
Okay.
By an outside force.
Bingo. Aiden already knew. How'd you know that?
Well,
Where'd you hear that from, or how do you know that?
He guessed.
well, I watched the massive amount of war movies. I watched videos on war movies,
Okay.
debunking certain things in war movies.
So like the
You hear
missiles.
physics a lot.
Nice. That's great. So Aiden's right. He said an object in motion stays in motion unless acted upon by an outside force. Now we'll come up with a even more specific definition. You don't need to worry about that now. I'm going to set you up for what it is. So the first law is it will continue in its present state of motion unless acted upon by an unbalanced external force. Right? It has to be a force that acts on the object to change its state of motion. And it has to be unbalanced. Right? If I have my marker on here, if I push with an outside force with nothing to balance it, I change the state of motion. If I push on both ends with the same force that they cancel out, it doesn't change its motion because I'm applying a balanced force. Josh?
So like if you were in space, let's say theoretically you shot a gun or you threw a ball or something like that, wouldn't it just keep going on indefinitely?
Yes.
Because there'd be nothing to slow it down or
Yes.
stop it. It would just go on forever at that speed.
Yes.
Does that also mean like would it not accelerate?
Correct.
So
If
it's
you
whatever
fired
speed
a gun in space, one, that explosion is the force that can act on the bullet. Once that bullet leaves the gun, there's nothing acting on it. There's no air resistance to slow it down. There's no gravity. It would just keep going at the same speed forever and ever
What speed would
until a force acts on it. It could hit the gravity of another planet and change its path.
World War III with the Martians.
So that's a good question.
So that means
The second law, again, we'll talk about this later. How could you summarize this law really simply? As in, what equation could you write that is the same thing as this sentence? Bingo. F equals ma. It said the force equals the mass times the acceleration. This whole law is literally just F equals ma. We'll get to that later. The third law, every action, there's an equal and opposite reaction. Right? If I punch a wall, my hand gets hurt because the wall applies a force to resist me.
If you punch it hard enough, it put a hole in the wall.
Yes.
It'd be the opposite.
You still feel the same force that you're applying. It applies that back, but it can't resist the motion that causes it. Again, we're focused on the first law right now.
Let's test it.
yeah.
You should go there and punch like that.
I will be something.
You guys, you've heard of this word, right? We've heard of mass. We've heard of weight. You've heard of volume, right? You know what volume is? How about density?
There's a lot of people like that.
Have you guys heard of specific gravity?
No.
That one's probably new. That one's very nuanced. Mass, right? This is not identical, but the same thing that I just showed you. It's a mass scale. This is to identify how much mass an object is. The mass that I put on this scale that balances a known hanging mass lets me figure out how much mass my object is. That's how I knew my toilet paper was 60 grams of mass, because the mass that balanced it was 60 grams. Mass is just how much material or matter there is. What are the units? Huh? Grams. In physics, we'll typically use kilograms, but they're the same thing. It's just a fraction of the other, right? Pounds is not a mass. I want to repeat that. Pounds is not a measure of mass. What does pounds measure? Weight. And what is weight?
How the gravity pulls us down?
Yeah. What is that? The general sense. The blank of gravity.
The pull.
Force. Yeah, that physics word, exactly. Kilograms. Here we have weight. It is a force. What force do we use in science classes?
Newton.
Newtons. Bingo. Newtons is the metric measure of force. Newtons and pounds are the same thing. They're just a different unit. So we're going to be using kilogram for mass. We're going to be using newtons for the force. This is a spring scale. That spring is measuring how much force gets pushed down on the object to tell you its weight. If I ask for the weight of an object, I want that answer in newtons. I want that force, not in kilograms. That might trip a couple of you guys up for a while. Force and mass are related. Gravity acts with a certain amount of force on mass. If you have 1 kilogram of mass, gravity is pulling on it with exactly 9.8 newtons of force. It's actually 9.81, blah, blah, blah. They can measure it very accurately. Forces, at least gravity, weight, it acts on an object no matter where it's at, right? Earth's gravity is the same. Any amount of mass, gravity pulls on it the same amount. Have you guys heard about the moon? How you weigh different amounts on the moon? You guys remember that? Do you remember the magic number? How strong, how much lighter would you be on the moon than you would be on the Earth?
You say it's like 6.8.
Yeah, it's about 6.
Oh, I just guessed.
Yeah, the moon's gravity is about, I'm pretty sure it's about 1/6 of the force on Earth. So 1 kilogram, the mass, weighs 9.8 newtons on Earth. But on the moon, that same mass would only weigh 1.6. Sorry, that's kind of in the top. Right? The force is the weight, how strong gravity is pulling on it, but the mass is exactly the same. If I had an object, how would the masses compare on the Earth and the moon? The mass. How would the masses compare on 2 different planets? Let me help you out. What is mass? The mass of an object, what is it telling you? Come on. No, that's weight.
Density.
We're not quite there yet. That's something more specific. What does mass tell you? If I tell you it's 5 grams, what is that measuring?
The I'm trying to think of
You've probably done it in chemistry class.
Oh, I had a bad chemistry teacher.
Okay, mass tells you how much matter is in something. It basically is adding up the mass of the atoms in that object. And we won't go that specific. Does the amount of matter in, say, a tennis ball change if I take it to the moon? No.
No.
I don't lose material on my tennis ball. It's still the tennis ball. The mass is exactly the same no matter what. But the weight of that tennis ball would be different. Gravity of a planet creates weight. It's the force that pulls on an object. If you change the planet, you're changing how strong that gravity is, and therefore changing the weight. Volume. We should know this one. It's essentially how big something is. How much space does that object take up? Right? When in chemistry, you have a graduated cylinder. You measure it's 85 milliliters. That's a size. It's a volume, an amount of space that object takes up. Does anybody know the metric unit for volume? I'll maybe give you a hint. Volume is a 3-dimensional measurement.
Meters.
Huh?
Meters.
Yes, that is one, but basic SI unit, the standard measurement. To calculate volume, we would take length times width times height.
Cubic meter.
I heard it, yeah. What do we measure length, width, and height in physics class? What's the base unit, the standard?
Meters.
Meters. So if my volume is length, width times height, and I measure distances in meters, wouldn't it have meters times meters times meters? You'd have cubic meters. Right? So you literally had a meter stick. You did a length and a width and a height, and you made this cube. That would be 1 cubic meter of space. It is. A cubic meter is huge. That's also why, anybody ever poured concrete or been around people that have poured concrete? What do they measure the concrete in? Do you remember? They measure it in yards. They say, I need 5 yards of concrete. Well, what they actually mean is 5 cubic yards. It's if you took a yardstick and did the 1 yard long, 1 yard wide, and 1 yard high, that cube of concrete, that's a cubic yard of concrete. So then if you think to pour your driveway, I don't actually know an accurate estimate.
Depends on how long your driveway is.
Yeah.
My driveway is very long.
Even a short driveway could take like 20 cubic yards of concrete. And you're like, well, it's only like this thick. But think of how much space it takes up. You're having to pour, the width of your driveway all the way down. That's a volume. You ever seen on cereal boxes? They have 1 pound, 2 ounces. It's not the ounce in your measuring cup. This is a English, U.S. unit of weight. There are 16 ounces in 1 pound. This is actually measuring the force of that object. Not the actual, how many cups it is. Density, we heard earlier. Density combines 2 quantities, mass and volume. Density is telling you how much mass do you shove into a certain volume. Right? I could have a cubic meter of feathers. There's not a lot of mass to feathers. If I pack that same space, it's not going to have a lot of mass. But if I have a cubic meter of sand, there's going to be way more mass in that same space than the feathers. which one is more dense? Which one has more mass in the same amount of volume? The sand. Right? This is why things float. If I throw styrofoam in the water, that styrofoam is less dense than water, so it doesn't sink. If I put a chunk of lead in the water, I don't know why you'd have a chunk of lead. If you threw it in the water, it's way more dense than water. It causes it to sink because the water can't support it. You can calculate density yourself. It told you, like, I have a 5 kilogram car or book that takes up 0.3 cubic meters. Well, you can tell me the density. Just take how much mass divided by the volume that you have. What is going to be my units for density? This should help you. What units are mass measured in? Kilograms, right? What did we just say volume was measured in? Meters cubed. Well, shoot. Those are my units for density. My basic units I'm going to measure in kilograms per cubic meter. It's going to tell me how much mass is jammed into every cubic meter. This is the Greek letter rho. It's basically like a P. When I write rhos on my paper, I do it like this. I can't write a P and make it look not like a P, so I have this tail. Whoops. And that's pretty common. So if you ever have to write that down, I would suggest write with a little tail. That way I know you're talking about density because you use that Greek letter rho. For mass, we just use a lowercase m, and V, we use a capital V. We talked about MKS's. MKS, don't worry about that. So these are different metals: zinc, lead, aluminum, tin, copper. What they have here is the exact same mass. All these have the exact same mass. But they're different sizes, aren't they? Which one of these is the most dense? Why did you say that?
Lead is very dense. Because it's small.
It's like circular reasoning. Well, give me more than that. What were you saying?
It's got the most mass in the smallest volume.
Exactly. If my mass is the same, what happens when I decrease the bottom of a fraction? Doesn't my number go up? If I pack 5 kilograms in 1 cubic meter, that gives me 5 kilograms per cubic meter. If I pack that same 5 kilograms in half a cubic meter, what's 5 divided by 0.5? How many times does 1/2 go into 5? 10. This density would be 10. I'd have a much more density. So there are actual densities. In 1 cubic meter of lead, right? 1 meter by 1 meter by 1 meter, a cube about this big, there's 11,000 kilograms. For reference, I probably only weigh like 100 kilograms. It's an enormous amount of mass in a small space because it's so dense. This is why we use aluminum to start building cars. Aluminum is very light compared to steel. Well, if you have a lighter car, you get better gas mileage. This is properties that we consider. This has a certain density, right? It's got a set amount of mass in a certain volume. What happens if I just smash that up? Did I change the mass of my bread? No. It's the same amount of bread. Did I change the volume?
Yeah.
Yes. I squished the volume down a ton. Did I change the density? Yes. Because density is mass over volume. If I change either of those, I change my density. Whoops. Volume decreased, density increased. I have the same amount of mass, but in a lot smaller volume. There's more mass per volume, so my density goes up. Mass always stays the same. This is just a summary. Oh. Weight density gets weird. mg is the force of gravity. Right? F equals ma. G is the acceleration of gravity. Well, if I know the force is mg, this is a force. So this tells me not my mass density or density, it tells me my weight density. How much force is packed in that volume. Then when you do something called specific gravity, we won't use this a ton. It's the ratio of, if I have a certain volume of an object, I figure out how much it weighs, and I compare it to how much the same volume of water would weigh. It's basically a way to standardize. Do you see this? M over V is density. So I have M over V times V is just mg. So you can simplify it to just compare the densities. Okay, again, we won't use that a ton. It's just you need to know what it is. This is a big word, a new main topic, but it's really simple. Is what? Say it again.
The property of matter.
Inertia is a property of matter. What is that? Bill Nye, right?
Bill Nye.
Yes.
Right
He
there.
says that like
In the intro,
golf
inertia
monitor.
is a property of matter. Bill. Yes. Bill is actually right.
It's more possible.
Inertia is a property of matter. Specifically, inertia means how resistant an object is to changes in motion. Right? When you play, I keep thinking of my football practices as a kid.
Cornhole.
Wait, what?
Cornhole?
Is that, what drill is that? I might be taught, is that a drill in football?
No.
No?
Normal like bags.
That's,
Right, you don't call it cornhole, do you?
we do, but I was talking football and he said cornhole, I was like, is that a
Oh,
football
no, I was
thing?
thinking more of
So,
backyard cornhole.
one thing my dad would do, my dad was my football coach, and he had this drill where everyone stood in a circle. This was pretty messed up. Yes, he would literally throw the football to somebody, and you had to run, if you caught the ball, you had to run straight across and run into someone and try to get out of the circle. Well, that other person tries to stop you. If I get the football, and I look across,
No.
say I see Andre, Sierra, and say Brody. There's three choices. Who should I try to run through?
Probably not Brody.
Not Brody.
Not Brody.
Go for Brody.
Why not Brody?
Because
No,
he's
I
the
should-
largest man.
He has a lot of
I
mass.
go for Brody.
He's a big guy.
It is so-
Brody is a big boy.
What's Brody's inertia? He has a lot of resistance to a change in motion. If Brody stands there, right, and you try to run into him, he has a ton of inertia. He will resist a change in his motion a lot. Well, I might bounce right off of him because I couldn't overcome his inertia. Inertia is related to mass. Have you ever seen car crashes? Which car wins?
My car.
The big boy.
The big car. This is why parents want their kids to drive big SUVs. They suck on gas. They're more expensive to own. But sometimes parents get their kids a big SUV because they are massive. If you get in an accident, you have a lot of inertia.
And then
And
there's
it-
kids drive around a Chevy Spark.
Yes.
You drive like a
Have you seen smart cars?
Yeah.
You know what smart cars are? They can literally pull straight into a parallel parking spot and fit. They're literally like this long. They advertise.
Tug of war.
Arvo spotted this one.
Have you ever seen videos of people doing tug of war with smart cars?
No.
Yeah.
Do the smart cars get wrecked?
Yeah, like they'll get like 10 big dudes or whatever. Just pull
Yes,
together,
yes.
And they'll
So
fight
the
each
one
other.
thing that there is a smart car commercial that advertises the strength of that car. They literally take a Suburban, a huge car, they put it on the frame of a smart car. And the smart car doesn't collapse. That's very impressive. As a physicist, when I think through, you're right, it won't collapse. But what happens if that car gets in an accident? I have little smart car and massive sedan driving at the same speed.
It goes right through.
Who has more inertia? The Suburban will literally, the Suburban will barely skip a beat, and it'll just plow into your smart car and send it careening the other way. That smart car does not have a lot of mass, therefore it does not have a lot of resistance to a change in motion. It can't fight back very well.
Imagine driving a glorified Belmont car.
So even though that smart car is strong, it won't crumple, you're going to get major whiplash. Because you're going to be going 20 mile an hour, that sedan's going to hit you, and you're going to get whipped forward and shot the other direction. That will hurt you greatly. Yes, it will do bad damage. That's why smart cars, for as strong as they are, you can't escape physics. It's not going to be safe in a collision.
Maybe they make them heavier.
Technically. But they only have like a 1.2 liter engine.
We're just gonna stick weights in the back of the truck.
So you guys,
Take those weights.
what is a change in motion? You can still
Acceleration.
see it. Dang it. Does that make sense? If my position is changing, that I have velocity, right? I'm moving at a certain speed. My motion's not changing. I'm going the same speed. I'm just in a constant state of motion. When I change my motion, I either speed up or I slow down. So inertia really is a resistance to acceleration, right? We talked about this. Inertia, a resistance to acceleration or a resistance to a change in motion, directly related to mass. Mass and inertia are almost interchangeable. But mass means how much matter there is. Inertia means how resistant to a change in motion it is. If you talk about inertial mass, they're basically just mashing these two into one concept since they're basically the same. Which ball would hurt more when you try to kick it? Now you can answer, well, hopefully not from experience. I hope you haven't experienced how hard it is to kick a bowling ball. Why is the bowling ball more painful?
It has more inertia.
It has more inertia.
Why do you kick one? You tell me which.
I was going to say we got one. Does someone want to volunteer?
I
No.
got it.
We're not going to kick. I would probably get sued by your parents. Most definitely.
Andre would get lawsuits.
Does this make sense? If I can kick with a certain amount of force, I want to kick the object that can't resist my force very much. Well, a soccer ball doesn't have a lot of mass.
Unless the soccer ball is full of concrete.
That's true. It would have more mass and therefore more inertia. And it would hurt me much more because it fights back easier.
Or inverted metaphor.
More mass, more inertia.
Which one would be worse then? A bowling ball or a soccer ball filled with cement?
Oh no, why don't
We're going to depend on how much cement, how much has to
Did you guys see these animations? Watch the object on the left. They hit it with a certain amount of force. Then they hit the one on the right. Which one had more inertia? Why do you say that?
Because it moves far.
It didn't move as far.
Yeah.
Yeah. Say it again. It resisted a change in motion. It resisted acceleration much more than that one did.
Wait, can you even like measure inertia?
Yeah.
Concrete, mass.
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 Okay, mass would be the reason for that.
Mass is literally directly proportional to how much inertia an object has.
So I was just wondering, like, I was like, you don't just say, oh, well, this thing has like 20 inertia. 20
No.
units of inertia.
No, it doesn't. We're going to talk about F equals ma, and we're going to see where that inertia pops up. We're also going to later talk about momentum. Momentum is a more specific or detailed look at the inertia of objects.
So
We'll get there in a bit.
So, like, if you had, like, I don't know, if you had something that could have a lot of inertia, if you take something that goes, like, really, really fast, like you take a bullet and you shoot that object.
Yep.
Even though the object that you're shooting at might have a ton of inertia, so it's, small,
Yes.
super faster.
Well, what you're talking about is we're going to look at kinetic energy, which takes it in how much mass an object has and how fast it's going. And then you can do the same thing with momentum, which looks at mass and volume. And the car crash, we're going to bring that back up when we talk about that. So hold that really quick, yes. Free fall. Have you guys ever seen or heard of they drop
Tom Petty.
No, they drop a bowling ball and a feather
In a vacuum.
in a vacuum?
Yeah.
Oh, shoot. Which object has more mass?
The hammer.
The hammer. There is more matter in the hammer. Which has more inertia?
The hammer.
The hammer, because it has more mass. Which one resists acceleration better?
The hammer.
The hammer. Why?
Because it has more mass and more inertia.
More inertia. Even though mass is directly related to inertia, again, AP could ask you this. Which object resists acceleration better? Why? You would say the hammer because it has more inertia. If you said because it has more mass, they might not count that. Inertia is defined as resistance to an acceleration.
So, like, saying mass is right, just not, like, specific.
Yes, it's right, but you're missing a step, basically.
Yeah.
Yeah. And I only bring that up because, again, AP will sometimes use those nuances, and so I'm trying to enforce very specific definitions that we can use. Which force of gravity acts on it greater?
The hammer.
The hammer. Isn't that right? Doesn't gravity accelerate objects exactly the same rate?
Yeah.
9.81 meters per second squared? Well, to get those two objects moving at the same acceleration, doesn't gravity have to work a lot harder to move the hammer the same rate as the feather?
Mm-hmm.
Why is that?
Because it's going to resist.
It's going to resist more. The hammer has more resistance. Gravity has to work harder to move the hammer because it has more inertia than the feather. So here's the tricky question. I kind of set it up to give it away, but in a vacuum, which one accelerates more or goes faster? In a vacuum. What do you guys think? The hammer? The feather?
I think the
Any other thoughts? Both? Do you think the same?
I don't know.
On the way down, the hammer.
Aiden's right.
Okay, yeah, that's why.
This is weird. If I go on the top of the building, I drop a hammer and a feather at the same time, which one will obviously hit the ground faster?
Hammer.
The hammer. Did you know the only reason that happens is because of air resistance, which is the thing we remove to simplify problems? Again, real physics gets very complicated. If you're in a vacuum, you don't have air resistance, gravity is going to accelerate them exactly the same.
So both have to go at the same time.
Yes.
So does that mean
Oh, I don't have that video. Dang it.
so weight doesn't matter? It doesn't matter if the object's weight, like,
in terms of measuring how fast it accelerates, it's true that it doesn't matter.
So like, just assuming air resistance is an issue. You like have like a 100-foot drop and you drove a sedan off versus then you threw a penny off, they both hit the ground at the same time.
Yes. If you didn't have air resistance. Because gravity, the force acting is different. Gravity works way harder on the sedan than the penny, but it accelerates, it moves at the same rate. So this is an example. They have this massive vacuum chamber. It's like a huge silo that they can suck almost all the air out of. And what they're going to do is they're going to release feathers and a bowling ball at the same time. This one, I think, is in air, so it's with normal air. That's what happens in real life. The bowling ball hits way faster. Now, this is in a vacuum. All the air has been sucked out. And this is freaky. They're falling.
Wait, is this?
It's in slow motion.
Yeah, it's in slow motion.
Okay,
Yes. We're not in
Maybe
space.
that'd be really
That's a
weird.
good point. Slow motion.
No air, no gravity.
I was covering this up. Look at that. The feather and the bowling ball are at the same place. They're accelerating the same rate. Any moment in
Only 'cause
time.
they're longer.
The birds are longer jump.
Everybody gangster until
It's not the
Angel
bowling ball's
comes in.
So
fault.
what?
Until Angel bowling ball comes in the room.
So
Because the bowling ball was again.
that's a weird thing, but air resistance in reality affects our motion. A lot of our problems we remove it to simplify our equations.
So wait, if two objects had the same like aerodynamics, but one of them had more mass, what would happen?
They
Explode.
the same aerodynamics. That's a good question. That has me thinking two different ways.
I feel like if you just because we've been talking about cars, I feel like if you took two of the exact same vehicle, one you remove the engine, you remove all the seats and everything, so it's still the same. It still takes the same amount of space. It still have the same shape, but the one with all the engine and all the interior would be way more.
They would be the same. They would be the same. Because they have an equal amount of drag. That's the same. The force of gravity would be a lot bigger. But the problem is this has more mass.
Right.
So they would move at the same rate, but gravity has to work harder for the heavier object. So the answer to your question, they would fall at the same rate. It's just gravity has to work harder on the heavier object to accelerate at 9.81. And we'll get to that with F equals ma. If you could even do this, do F equals ma for two objects, but one of the objects has 2 times the mass. We'll do your equation and realize g is constant. If I have double the mass, I have to have double the force to keep gravity's acceleration. That's it. That's a great question. Again, this is review. Again, so far we're just focusing on force vectors and Newton's first law. Where does inertia come in? Into Newton's first law, which says it'll continue in its state of motion unless you act on it with an unbalanced external force. How does inertia play into this law?
How much external force is needed?
Yeah. Why? What phrase relates to inertia? Remember, inertia resists a change in motion. Well, right here, it stays in whatever motion it's in unless you have an unbalanced force. This is the inertia. Right? It would also stay at rest or in steady motion unless you add a force. Right? If your plane is moving at 500 mile an hour and this kid gets a bowling ball on the plane, takes it out of his carry-on, pulls out a 16-pound bowling ball.
One of the saddest pictures I've ever seen.
And he threw it.
He said, this airplane is going fucking miles an hour. All I imagine is this kid out on the...
Which one happens?
Wait,
The second one.
what did you
So
say?
the first option,
So much.
the first option is he throws the bowling ball straight up and it shoots back
No.
because the plane's moving at 500 mile an hour. The second option is he throws the ball straight up and it comes up and he catches it.
Yeah, that's what would happen.
That's
Why?
right, because it's already moving at 500 miles an hour with the rest of the everything else.
That's
So
right.
the air inside of it is still because the air is already moving at that speed.
Yes. Relate that directly back to Newton's first law.
Well,
You
I
were
mean,
the
you're
math.
like, so
Everything is already in motion, so it's going to stay in that motion.
Yes.
It's not going
Now-
to stop for some random reason.
He changed the motion, didn't he? He threw it up.
We changed the
He
y
yes.
Well, you wanna know
He
what
applied the force in the y direction, accelerated it, gravity pulled it straight back down to his hand. There was acceleration in the y direction because he applied a force. If he throws it straight up, nothing's acting in the x direction. There's no unbalanced force to change the x direction motion. Therefore, it just comes straight up and back down.
The only way for that to happen is if like the plane had like a top on it or something, and then would it like fly back?
Yes. Or say you're in the back of a pickup truck and you do this.
Yeah.
Well, if I throw it up in the back of a pickup truck, well, all that air running over the car is going to shove my bowling ball backwards.
But if you're inside of cars, you can do
Wait.
that.
Yes.
Wait, but also wouldn't that be the same for like, so the Earth, it's going at a certain speed as it's rotating?
Yep.
Yeah.
So if that were true, that like things just like took off like that, then anytime you threw anything, it would just like.
Nobody would be on the Earth. We'd all just be like millions of miles.
Have you heard of the Coriolis effect? Coriolis effect,
Australia is totally spin the other way.
I think so. I know it related to snipers. Snipers that shoot long distance, they take into account the rotation of the Earth. If they shoot a bullet straight and the Earth's surface is rotating beneath it, well, it'll look like my bullet goes like this. Well, I shoot it straight, but my Earth actually rotates. Right?
Right.
So if my target is dead ahead, but it's such a far distance, I actually want to aim over here so that I shoot my bullet and the Earth will rotate and move the object into that direct path.
That's why snipers got such a hard job.
Yes. Sniping long distance, they take into consideration temperature, wind speed, wind direction,
Humidity.
Coriolis effect, humidity. It's ridiculous.
And then
But-
also, wouldn't the curve of the Earth also be an effect
Yep.
as well?
Actually, the Coriolis technically might be the curve.
Would it be?
What about gravity?
I don't know if that was all in the same umbrella or not.
I apologize because I might be misremembering what exactly the Coriolis is. It's either the curve or the rotation. And I apologize that I don't remember
effect is like.
100%.
Never mind. I don't remember.
Come on, Andre, tell us, okay?
Anyway, fact check me on that.
But I thought the Coriolis
And-
effect was like something about
Fact checkers all over.
like directions.
The spiraling?
Circles.
Yeah. We will.
I just know that from the Simpsons.
Now you got me. I hate
True, guys.
misleading you guys also. I hate being.
Coriolis effect
I hate
is
spreading
about
false
the reason why
information.
If you flash your bullet in Australia, it spins a different way.
Can that also just do with the direction which the
Yeah,
water
yeah, it's the
falls in?
rotation.
Yeah.
So I wasn't wrong. And I don't care about being right, I care about not misleading you guys. I'm not arrogant and I have to be right all the time. I hate being someone that misleads you guys.
I'm a teacher. I'm right. Listen to me.
Exactly. Do not ever agree with what I say because I'm a teacher. One, that's garbage science. That's how the world gets misled by fake science.
That's why we got coronavirus.
We won't break open that can of worms.
That's why we've got anti-movement.
Right?
That's why we have what?
It looks like my object's motion curves,
That's wrong.
but it's because it's going straight and the Earth rotates. So if I track the path of my object on the Earth's surface, it looks curved. Okay. So I think I want to end there. I don't want to take on too much more. Oh, here's a good one. Oh, shoot. Not from start. Hold on. I know. There's a lot. Do I got 7 minutes left?
You got like 10.
10?
Oh wait,
Is
you
it
got 40 or 45?
45? Okay, okay.
You got like 10.
You got you got like 11.
Okay. Do you see this? There's this huge elevated like highway that was on these concrete pillars, and it tipped over to the left. Which way did the Earth shift suddenly?
It shifted to the
right.
right.
You're saying this way?
Yeah.
Why do you say that?
Because this object
Because
is
then the
still,
force
and
would
so
have
when
went
it
that way.
moves, it's going to want to stay still. And
Yeah.
Inertia.
What causes this road to stay still when the Earth suddenly shifts below it? What property?
Inertia.
Inertia.
Okay, let's go.
Yes. Inertia is a resistance to a change in motion. Well, if I have this sudden motion this way, I have a lot of mass, therefore a lot of inertia. It resists motion. My bridge wants to stay here even though my Earth shifted out. Well, then there's no concrete pillars underneath and it just falls.
Is that like when you pull a table?
Yes.
it's like everything's like
Yep, when you have a huge table with fancy decorations and glass and china and whatever, and you take that tablecloth and you yank it,
It'll fall over
me too, what happens is that tablecloth gets yanked out from underneath, and there's not a lot of friction that gets applied to those objects, and so it kind of slips past. But also, those objects have inertia. They do not want to just slide over and tip. They want to stay where they are. And so I have this quick motion, creates a little bit of friction. They might jostle a little, but they want to stay there. Another really great example, well, one, I'll show you this, right? There's the gravity. Gravity's pushing it down. Well, if I move my support from underneath, there's nothing to hold it up. Gravity wins and shoves it to the ground. This guy.
Hold up. What?
How did this happen?
What?
oh, he was moving real fast and he stopped suddenly, and so the boat kept going.
Boom! Does that make sense?
That or didn't strap
He
down.
hit a pole.
Boat no stop.
He was pulling a boat and he hit a pole. Well, that pole's stopping his car dead in tracks.
I don't think.
But wait a minute, his boat's still moving. His boat broke the hitch. The boat had inertia.
That's the most.
The boat didn't want to stop. It did not want to change its motion, so it just kept on going
You must
until
have not
something stopped it.
down.
Rammed up on the car.
Or the strap broke. Either the strap broke or didn't strap it down. There is like
Why
a
would you
hook
strap
in
it
the
down?
front.
I think he's better off now. I think he should just go straight to the lake like this. He doesn't even need to hitch.
Well, yeah, and then he
Easy peasy.
His truck's already
There's
trapped.
an
Just
accident
drive
outside
into
my
the
house
lake
because
or
I live by
whatever.
a and there were three semis and a car, and the truck didn't stop, ran up the car into the back of another semi. We couldn't even tell there was a car.
Yeah, it's scary.
That was just like 2 or 3 weeks ago.
And that's because that car has inertia and nothing's stopping it until it hits something big and it just keeps going.
The last semi ran up and went into the back, into
No,
the middle.
imagine that, and then like the boat or the boat's tied to the truck, so the truck's like moving
That's how
underwater.
screenshots work too.
What is this?
So,
What?
in an accident, say this lady is in her car.
Okay.
What happens when you get into an accident? Say this lady got rear-ended. Some car smashed into the back of her car.
She goes, you going.
She gets it back.
Which
She
direction?
goes back.
Like this?
Yeah, she goes back.
No.
Why?
She gets hit in the back.
If she gets hit from
Because
the
she gets
back,
like pushing.
Yes.
if she gets
She
hit
gets
from the back,
hit
she's
from
gonna go
behind.
back.
Yeah, she can go backwards.
Why?
Because when she gets hit from the back, the car keeps moving forward, and she wants to stay there, and so she gets.
Yes, she has inertia. She wants to stay where she's at. She's at a stoplight. Some car just smashes into her. Well, the car receives all the energy. It gets shoved forward. But I'm just sitting in here. The only way that I move is if something moves me. Well, my car's going to move forward until it hits the headrest.
What?
The headrest is what then hits me and prevents my neck from basically just keep going that way. Seriously, people, you can, I won't even say it. That's literally why a headrest is a massive safety feature. It basically prevents you from snapping your neck off.
And like older vehicles didn't have that, just like a splat.
Yes, super dangerous. Now you can't do anything for moving forward. How about in a race car?
You could put.
They have the like.
Yeah. Right? It's called the Hans device. Head and neck system, basically, is what it's called. Hans device was a massive breakthrough in safety. Their helmet is literally attached to a collar in their, either mounted to their chest or mounted to their headrest.
Mounted to their.
If they got rear-ended, they have their headrest that stops their head from getting whipped back. If they hit something, they're going to want to keep going forward. Well, you need to stop your head from whipping forward. So they attach it to either a mount on your chest or the seat rest itself, so that if you hit something, you move forward and those restraints stop your head from whipping forward.
The problem is your brain is still going to be alive.
That's the
That gets great into like biomedical engineering stuff where you have to understand how the human body works, because you're right. Your brain has inertia. Your brain's sitting in your skull. If I hit something, my brain's going to want to keep going the speed that I was until something hits it. That's the front of your skull.
That's some of the bigger issues.
Yes. That's why, guys, yeah, that's why concussions in football, that's what's happening. When you hit somebody or somebody tackles you, they say they tackle you, they launch your body this way. Your brain has inertia. It wants to stay right there. The front of your skull smashes into your brain and rams it backwards. You damage your brain from that impact. That's where your concussions are coming from. Aiden?
The Hans device is connected to the seat.
Yep.
That's actually how Dale learned right back.
Because he didn't have one or it
He
failed?
did not have one.
Yeah, okay. I didn't know that.
It's actually because of that, Rick, that they have it.
Really?
Yes.
That was the catalyst to install Hans devices on every driver?
Yeah.
Well,
required.
sadly, it would take a tragic accident to motivate people like, hey, this isn't just a stupid safety thing. It's, legitimately a safety feature. Yeah. That's why a seatbelt works. What do seatbelts do for you?
You keep from going zoom out the windshield.
Bingo. If I run into a brick wall, my car's going to stop.
Wait, but if you're
But
driving
I
a
want to keep
heavy
going, and I'm
enough,
going to
big
smash
enough
into it.
vehicle,
The brick
if
wall.
you're driving a heavy enough vehicle that's big enough, you can just go straight through the brick wall.
You could.
So-
You still have that brick wall is going to still apply a force on your car.
Not if you're not vehicle.
No, it will still apply a force on your car.
If you have a big enough vehicle, it'll be very minimal compared to
Yes.
this car.
The effect of that force decreases if your car has a lot of inertia.
So essentially, if you just drive around the most biggest, heaviest, obnoxious thing you can possibly find,
That's why semi-truck drivers have to be really careful, because if they run to the back of a car, they don't feel it very much.
Yeah.
It just kind of moves the car out of the way.
My grandpa said he hit a deer with a grain truck, and he said he's hit it, but he couldn't slow down in time for it. So he's like, all right, I'm gonna slow down a little bit, but I'm not gonna
plot it.
Yeah.
He said he just smacked and just kind of flew off into the ditch 30 feet. And
Yeah.
put a dent
Yeah,
in
it
the
gets-
bumper. Just put a dent in the bumper. Or whatever,
Yeah,
and
because that truck has an insane amount of inertia. It's not really
it didn't,
affected
go
by other
over.
things.
It's kind of
But then you can't stop it, so you just go over.
Oh.
That's like 80,000 pounds.
All right, how about this one? Right?
What? I missed it.
All you're doing is driving a straight line.
Yeah.
What happens if I crank the wheel to the right?
You're gonna
I'm
want to
going
keep
right.
going straight. You're gonna
Exactly.
slide.
If I drive my car and I want to turn, watch what my body does. Right? I'm going straight, and then I start turning. This is what my body wants to do. Right?
If you don't have your seatbelt on or a door, that's what's gonna happen.
This is why if I'm driving and I crank to the right, Sometimes I hit my head on the left. Or if your mom or dad or whatever's driving, and they all of a sudden swerve, you smash your head on the opposite window.
They do that.
That's because your body's going straight. All of a sudden your car moves. Well, you're not moving yet. Nothing's causing you to move. Well, it's not until you keep going straight and the window hits you and actually changes your direction. That's because you have inertia. And it hurts.
Normally, you gotta like.
Yeah.
I'd be making them start prison.
So what somebody drills out, you push
Yeah, you whip one way and then the other. And if you're driving, you know the response, so you like counteract. That's why. Have you ever seen people that play video games and they use a steering wheel, like Mario Kart Wii, and when they race, they like go like this or like this. They're like, oh.
Because you think you're going to go.
They're acting out what they've experienced in a car. If I crank to the right, I go to the left.
That's how I drive.
They're acting out what they've experienced and what happens because of physics. Nothing's doing anything.
Have you ever seen
That's what they do.
That's how I drive.
Yeah. Also, disclosure, if I ever play Mario Kart Wii, I never use the steering wheel. I always use the nunchuck. It's so much easier. It's way easier.
You can use nunchucks?
Yes. So you plug it into the Wii remote and you drive with the control. Oh, it's so much easier. I beat my sister every time because I do that.
I have the Switch version.
And you can do it with the controller, right? It's so much easier. Yes.
You know what I do?
Okay, you guys, I have like 2 minutes.
I
got homework for you. It's not hard.
So you gotta get the notebook. That's one of them.
Yes, did you guys get notebooks?
Yeah, I
We
did.
don't need them right now.
Okay, have one.
I just need you to have one dedicated to this class. Yes, that's perfect. That's perfect.
And you said you wanted one that's like the size of the grid, right?
Yes, that's ideal.
Like
a
graphene?
composition with graph paper. Alright, the homework is posted. All I'm having you do is vector components. Remember, use SOHCAHTOA to practice breaking these up into X and Y. Then I'm having you read 2 short sections. It's like 2 pages long. And then there's just 4 questions. It's all on Classroom. You guys are going to do it on paper and turn it in. Virtual students, you're going to do it and then just submit a screenshot or a picture. Thank you guys. Have a great weekend. Seth, my man, what is